next topic is applications of Laplace transforms. So basically in this chapter what we're going to do, we're going to solve the electrical circuit by converting them into S domain. S domain is nothing but Laplace transform domain, and at the end of the problem, once we find the required parameter like voltage and current, now we'll convert it back into time domain by using inverse Laplace transform inverse Laplace transforms. Okay, so here is the first one. Inductor and capacitor, they both are time dependent quantities but not the resistor. So if you have an inductor in time domain, I of t, assume that I of t current is passing through this inductor. L is the inductor value. Voltage drop across the inductor V of t equal to L times di by dt. Remember, inductor can store energy in the form of magnetic field. Now when I convert this time domain equation into S domain, the inductance value, so in time domain it's just L, when it converted into S domain it's SL. Okay, and if there is any initial current passing through it, that value is L times I0 minus. That I0 minus is initial current. Okay, this is nothing but initial current. Some problems we might have that initial current is 0, so you're going to end up having only SL. That value is going to be 0. If you need to convert that into current source, then SL, the inductance is connected in parallel with the current source. Capacitance value is still SL, and the current value is I0 minus, so that's initial current over S. So depending upon the circuit, you can use either any one of these two. Most of the cases I'm going to end up using an inductor in series with the voltage source. Now when it comes to the capacitor, voltage drop across capacitor is V of t and I of t. So V of t equal to 1 over c integral of it dt, or it equal to c times dvt by dt. When I convert that into S domain, it's going to be 1 over cs. So the c is going to be 1 over cs, and if there is an initial voltage across that capacitor, that value is V0 over V0 over s. Okay, or I can convert them into a capacitor in parallel with the current source. Capacitance value is same, both cases 1 over cs, 1 over cs. This value, current source value, is c times V0. You can use the source transformation theorem to convert a voltage source in series. So this 1 over cs is kind of in ohms. Okay, so we can use the source transformation theorem to convert the given circuit into a voltage source in series with impedance. You can convert that into a current source in parallel with impedance. That's what we can do. Now resistance is independent of time. So the behavior of resistor does not change with respect to time, whether it is a DC source or AC source. The behavior of resistance is same. It opposes the flow of current, or it converts electrical energy into heat energy or light energy. So both cases V of t equal to, in time domain it's IT times R, in S domain R times IS. R value does not change in S domain. Now I'm going to solve go with a simple example. So here is an example, a series parallel combination circuit. Given source voltage is 275 times e to the power of minus 2t ut is unit step function, 1 ohm, 2 Henry and 2 ohms. Our goal is finding V0 of t, and here he also mentioned assume initial conditions are 0. So initial conditions are 0 means there is no current passing through the inductor initially. Okay, so basically when I convert this into S domain, here is an inductor. This value, the voltage here, is going to be 0 because there is no initial current passing through it. The first step, what we need to do, we need to convert the given circuit into S domain. Okay, so convert this into S domain. So e to the power of minus 2t is nothing but 1 over s plus 2. U of t is unit step function, and 2 Henry is going to be converted into 2s. Okay, and V0 of t is called as V0 of s. Now this 2s is in ohms, this is also ohms. So basically these two are in parallel. what I'm going to do, I'm going to find, say, I'm going to say this as zx. Okay, so that zx equal to 2s parallel with 2. It's going to be 4s over 2 plus 2s, or I can say 2s over s plus 1. Now, can I use the voltage division rule by to find v naught of s? So I can use the voltage division rule. If I use the voltage division rule, v naught of s equal to vn, which is 75 over s plus 2, times same impedance zx over total impedance 1 plus gx. So if I put that everything together, it's 75 over s plus 2 times 2s over s plus 1 over 1 plus 2s over s plus 1. Now v naught of s equal to, I'm going to solve it. So after simplifying it, v naught of s equal to 75 over s plus 2, 2s over s plus 1, and I'm going to do the common factor here, so I will end up with s plus 1 plus 2s over s plus 1. They both get cancelled out. So 75 times 2s. Remember, this is s, not 5. My 5 and s both look like same, so my apologies for that. So make sure that that's s. So at the end, I have 150 times s over s plus 2 and 3s plus 1. Now we need to convert this back into time domain. Okay, we can use a partial fraction. So by using partial fraction, I'm going to say this is going to be a over s plus 2 plus b over 3s plus 1. Okay, now to find a value, substitution method, since they're not repeated poles, or and those two are individual factors, so I can find a value, take the total equation other than the denominator of a and substitute s equal to minus 2. I have a value equal to 60 and b value, so 150 over s plus 2, substitute s equal to minus 1 over 3, and I have b value equal to minus 30. So I have v naught of s equal to 60 over s plus 2 minus 30 over 3s plus 1. Okay, I'm going to write it down s plus 1. So it's going to be 60 over s plus 2 minus 30 over, if I pull out the 3 from this denominator, 3s plus 1, I will end up with 10 over s plus 1 over 3. Now v naught of t, converting this into time domain by using the table, Laplace transform table, 60 times 1 over s plus 2 is e to the power of minus 2t minus 10 times e to the power of minus 1 over 3t, so t by 3, and unit step function u of t. Okay, this is v naught of t. Thank you.